Introduction. Good morning, everyone. I'm Leonardo. I'm a CS PhD student at Virginia Tech. Today I'll be talking about this paper called Evaluating the Impact of Point Marking Precision on Situated Modeling Performance. This work is co-authored by Professors Bowman and Márcio Pinho. Okay, so situated modeling is this idea of designing a virtual model over the real world. So imagine the user going to an empty terrain and designing a building right there. So they could use real neighboring structures like other buildings or pathways to aid their design. They could create a point over the corner of a building, for instance, create a point at the other side of the building, and then extrapolate a reference line that they can use to guide their model. And then they can keep creating references as many as they please, and once they have everything they need, they can start creating derived points over these references to define the footprint of their model. Once they have completed the footprint, they will probably want to transform this into a volume. So they could just create some points on a neighboring building, measure its height, and then apply it to the footprint, apply an extrusion to it. And then in the end, the user would be able to visualize their model aligned with the real environment. Okay, so why use situated modeling? Some motivation for it include being a less time-consuming process because it's no longer split, so you're not dividing surveying and modeling, you're doing everything at the same time. And it also provides the ability to make corrections on the fly. It improves the immersion and the perspective of the final structures, which is great for seeing sizes and proportions. And especially it preserves the relationship between the real and the virtual content. So you can see the alignment of the setbacks between the buildings and the model, the different heights. Okay, but before we move forward, we need to make a few considerations regarding 3D modeling. So the domain, such as architecture in this case, influences how we are designing this interaction technique. So in case of architecture, we have strong shapes, very definite lines, as opposed to other types of free sketching or humanoid modeling, where you have more organic shapes, that you care more about proportions. Then also technology plays an important role. So in VR, we always know the geometry of the environment. So let's say we have a room and we want to place a window over it. We can just use an interaction technique to point over the place where we want to create the window and place it right there very accurately. In AR, that may not be the case many times because the model may be unavailable or inaccurate, especially at larger distances. So we will have to estimate the placement of these elements. And finally, the dimensions of the model. So if we're modeling a mock-up over a table, we can use direct mapping, so we can use our hands to have a fine precision, and we can also use fiducial markers for tracking. On the other hand, when you're doing a full-scale situated model, you have to do at a distance interaction, otherwise we would need to walk quite a lot around the terrain. One way of doing this at a distance interaction is using model free-point marking techniques. So this allows us to obtain a coordinate in space without knowing the geometry of the environment. So in a prior work at Virginia Tech, we evaluated some of these techniques. Two of them are the geometric and vector cloud techniques. Basically, both of these techniques require the user to detect, to select a visual feature that they see in their field of view from two different perspectives. So the user would mark a feature from one position, move to the second one, and mark it again. The difference here is that vector cloud geometric uses only one ray from each of those perspectives, and vector cloud uses multiple samples. So you end up having this cloud of intersecting rays, and then you can just get the centroid and get a higher precision. So this work has shown that for marking individual points, vector cloud was more precise, especially at larger distances. Okay, some related work. Some previous work, like the bars and image systems, explore different ways of estimating placement and the creation of primitives, allowing us to define lines, volumes, working planes, and also others. But they do present some limitations that we will aim to contribute in this work. So the work in this area mainly was evaluated using formative studies, which are great for creating the interaction, but it makes a little bit different for us to understand quantitatively how they perform, compare, or how we can improve them. And we also have some questions regarding the point precision, point marking precision. So how does the accuracy errors propagate through the model? So we know that the techniques have different precision levels, but how does that translate to accuracy, and how does that translate to derived points on your model? And if those errors exist, does the user understand that they exist? Okay, so we designed a system to investigate this. We call it Modeling Architectural Structures in situ, or MAS. The idea is to use the point marking on existing real-world features and then derive points and shapes for the proposed building. These features could be the corners of existing buildings, as we saw before, and pathways. So we use the same geometric and vector cloud techniques. The difference here is that we proposed a new multi-point marking technique where we are able to mark multiple points from each of the perspectives. So instead of moving to both perspectives for every point, we are marking multiple points and then moving and marking multiple points again. So the user doesn't need to walk as much. And then, so then we built this for the Microsoft HoloLens and also use the Microsoft One controller as input. So the simple equipment allowed the user to go outside and create their model. We organized the tools under categories on a circular menu so they can be easily accessed by the user. And also we can see in the top right image there is a target, a crosshair in the center of the screen. That's the crosshair that the user uses to see, to indicate the point that he's trying to mark, or a virtual element that he's trying to select. Okay, so this leads us to our user study, where we evaluated the impact of the point marking precision on modeling. So our independent variable here is the marking technique, so we are going to compare geometric and vector cloud. In this case, we restrained vector cloud to 50 samples, just so we had a more constrained study. And this was evaluated within subjects. So our dependent variables were the accuracy. So we measure positional and angular errors of points and segments, and also the ease of use of the system. We had 22 participants, which were counterbalanced to minimize any learning factor. They performed a 1 individual hour session. And in this task, they had to recreate a building, so they would follow predefined steps. So everyone would make the same building, following the same steps, and then we would be able to evaluate the differences. While our system was designed to be used outdoors, we decided to perform the user study in a closed environment because we were able to replicate some similar environment, but at the same time much more controlled, so we can avoid problems with tracking, overheating, or sunlight. Okay, so our first hypothesis was that when using a less precise point marking technique, the derived points, not the ones that we directly marked, would have a significant accuracy reduction against using a higher precision technique. And our second hypothesis was that using a less precise point marking technique would reduce the ease of use of the modeling tools. Okay, so here I have a video that shows how the task worked. You can see a third-person view on the left and a first-person view on the right. So you can see the user is marking the point. He's moving now to second perspective, marking it again. Yeah, so he created 2 points, and now he has this reference line that is aligned to that real wall. So he would do this many times, and then he would go to the next step, where he's creating the footprint over this reference line. He's splitting the surface in two, because he wants to have a building with two different heights. Now he needs to know what's the height of the ceiling to do the extrusion, so he's marking a point on the top. Yeah, and it does the extrusion automatically. And then in the other side, he just did half of the other side manually. So during the test, they would follow a predefined sequence. They were 9 steps that would result in this building. They were allowed to undo their last operation if they desire, but they were instructed not to go back to a previous step. So if they detected an error in the end of the task, they wouldn't be able to go back to the beginning to fix the error. Okay, so regarding results. So this is an aggregate model showing, an aggregate visualization showing all the models created by the users, split between geometric on the left and vector cloud on the right. We can visually see that vector cloud is more tied up together. Why the geometric points are more spread out. So we also use a color scale to represent the positional error in each point. So it starts with green for no errors, up to red, which means 2 meters or more of error. I also would like to point out that you can see that the points on the right for the geometric, they are much more spread out than the ones on the vector cloud. Okay, so we did a two-way ANOVA with replication, and we found a difference between techniques, points, and also an interaction effect. We can visualize in this graph for each point, for the positional error for each point, that vector cloud was the average error was less for almost every point. We further performed 20 individual parity tests in every point with level of confidence of 95%. And then we applied a Bonferroni correction to avoid repeated measures randomness. So we found statistical significance on 2 points, points 8 and 20, which were the ones further to the right. And we also found differences when comparing each line segment against the ground truth and angular errors between connected line segments. We were not able to detect after the correction where these differences are present. Okay, so regarding ease of use, we also found differences when comparing each line segment against the ground truth. So regarding ease of use, for both techniques, participants misunderstood alignment errors. So they confused these errors with inclination, which we know was not possible because we constrained the terrain to be flat, so it couldn't be an inclination. And this is an issue for architectural model because a wrong understanding of the building may lead to wrong design decisions. So in conclusion, we evaluated the impact of point marking precision on situated modeling. Some of the take-home lessons here are that higher precision marking techniques resulted in a higher accuracy on the derived model, and that unlike what we were expecting, the technique did not directly influence the ease of use. We had problems with both of the techniques because of visual perception. But however, we do note that the amount of errors indirectly will influence the useness of the model. And for future work, we should work on techniques with high precision, but also less cumbersome for the user. Thank you.
Are there any questions, comments for Leonardo? Raise your hand. Mike. In a moment, I will I started one. So in your paper, you showed that one technique, vector cloud, is more accurate than the other one. But do you have any insights how accurate it is enough? I mean, you already showed that those techniques frequently result in errors over 2 meters. Mm-hmm. Yeah, I mean, vector cloud a little bit less, but do you have any insights? You talk to domain experts or other people to see what is an acceptable error for in this specific domain?
Right. So when we started this work, the first thing we did was talk to a lot of architects, and we defined that we were working with massing models. So massing model is a very initial state of the design. It doesn't require like centimeter precision, but at the same time you need to have the correct shape of the building. So an accuracy good enough here would be something that doesn't give the architect the wrong geometry, right? Something that makes it difficult for him to understand what's going on.
Do you have any insights that actually those techniques have an impact on the understanding of the architect then?
Well, yes. If the error, if you're using a low precision technique and you have a large error, it will be difficult for you to understand what's going on. So,
do you have evidence, or this is an assumption? Do you have evidence for that?
Mm-hmm.
So, do you have evidence that because you right now just quantified the error, but do you have evidence that this larger error actually impacts the decision of architects or other domain experts?
Oh, okay.
Is this something you consider in future work?
Yeah, no. That would be a future work, because we would have to work very closely with architects to make sure how much. Yeah.
Further questions?
Mm-hmm.
Actually, imagine like from architects that we notice something. There is probably either hearing or technology in the different hands. Architects will start from the setbacks and whatever was planning regulation allowing and go in that direction. But developers will allow your technology. You will allow them to visualize massing before they start. So developers are probably the target market for you. If I suggest if you are interested in learning more about it.
Yes, definitely. Thank you.
Any further questions? I have a second one.
Okay, yeah.
So you were already using an additional controller with an isophonic joystick. That's, as far as I know, the Xbox One controller. And did you consider using combined techniques where you actually can have a coarse initial, let's say, target acquisition with your head face-based pointing, and then combine it with the controller? That's something that you also consider.
Okay, so for these techniques, we just use the controller for selection and accessing menus and all of that. There is another technique that a colleague of us is working with, that you get a picture of the environment, and then you can use the joystick to move the cursor to the correct place and get a higher precision. Yeah.
Any further questions, comments? No? Let's get Leonardo another hand.
Okay. Thank you.